And hello YouTube, testing 1, 2, 3. Yes, we are live. So we are recording. So last video we were talking about the Peng-Robinson equation of state. Now, of course, we want to be solving this Peng-Robinson equation of state ideally in Rust. And through that process, we are going to find out lots more about how to code certain simulations in Rust. So we have a Peng-Robinson equation of state here. The thing looks kind of messy, but let's have like 3 scenarios, for example. So let me hold on for a little bit. Yeah, hold on. Yeah, let me go back to this. Yes, so we have this Peng-Robinson equation of state. We'll normally want to find one of three things. Excuse me. So it's pressure, the volume, okay, the molar volume, or the temperature. Excuse me. So, well, for pressure and temperature, it's quite straightforward. So if you take a look at this equation here, don't worry about the notes at the bottom first. Take a look at this equation here. We have P, we have A of T, V at the bottom, V on top, and this RTK over here. Now, if you want to solve for, let's say, pressure, it's quite straightforward. You just substitute all of these things over here, the volume, over here and over here. You substitute the temperature, okay? And you substitute both of these, okay? And you find your B, because B is kind of constant, assuming you know the supercritical properties, okay? And the eccentricity factor, you should be able to find the pressure given a temperature and a volume. So that one's the easiest, okay? You don't really need to solve it. You just shift the factors to the right hand side and you'll be able to find your pressure. The trickier thing is to find pressure given, to find volume given a pressure and temperature, and that's usually what's a little bit more challenging. And I guess even more challenging still, to some extent, you'll be trying to find the temperature given the volume. You'll be trying to find temperature giving volume and pressure. So you can see here, well, it's unlike what was here before. Okay, yeah, you can see here basically that hold on. Okay, you can see here that, yeah, there's a temperature term here in the reduced temperature. This reduced temperature is actually part of this A of T term. This T of K here is also a temperature. So we're gonna have a little bit of a problem finding temperature straight away. Okay, this there'll be a square root term right here. Okay, if you try and multiply this whole thing out, you will have square root terms and you will have a T term. Okay, the long and short of it, if you multiply everything out, you will have a square root. You have a square root of T, okay, because this reduced temperature ultimately contains this T term here. You have a square root of T, and you will have just T. Yeah, so within this A of T term, it's a polynomial in T of K, or rather the thermodynamic temperature. Okay, this A of T is a polynomial, so you have a square root of T and a T term. So if you actually expand this out, you will be able to get a square root T term and a square term. So that's essentially, if you think about it, it's a quadratic equation in terms of square root T. Yeah, if you have a quadratic equation, that is also pretty straightforward to solve. Okay, we'll just need to do some derivations for that. The most challenging one is the cubic equation of state. Of course, nowadays you have lots of numerical solvers. Okay, lots of numerical solvers. where you can solve it using Newton-Raphson method or some other kind of method to find all these three roots. Unfortunately, those methods are a little bit slower computationally. So there are thankfully analytical solutions, but they're pretty involved in themselves. So you want to look at the most so-called difficult problem first before you even solve the t problem, because the t problem is quite straightforward as we discussed. We have a t of k here, we have square root of t over here, and we have all the rest of the things constant. Okay, those that will essentially form a quadratic equation in square root of t. You will be able to solve for the temperature. Pretty straightforward. Okay, so that one we'll just use the quadratic root formula. You'll be fine. Okay, so that will only give you, I think, one temperature that sort of makes sense, because the other thing will be, the other temperature may be negative. It may be, I doubt it will be complex, but yeah, well, we'll have to see how things pan out later. Okay, so let's just focus on the volume. Okay, again, I was saying you can actually use other solvers. You will be able to find the suitable solution. However, those are slow, and I don't really fancy using them for the time being. So I want to use something a little bit more analytical, because it will compute faster. Okay, the thing about Rust is that you want the fastest speed. Of course, if you want to find roots, you can actually look at this roots crate. I will leave it in the description. It will have many root finding algorithms for you. You do not have to go through this if you don't want to, but walking through this cubic root finding formula will be a good exercise to start programming in Rust, especially with the what do you call that? With the unit safe methods. Okay, so for the Peng-Robinson equation of state, we will have to solve this cubic equation in the compressibility vector z. Okay, z is, for your information, PV over RT. So that is the z formula. So you'll have to solve this cubic equation of z if you want to solve for volume using pressure and temperature. So it will be z times some coefficients, and this you'll have this constant here. B equals to small b p over RT. What's this small b? Small b is this right here. This bp over RT. A is A times P over R squared T squared. Okay, so this is A of T. A of T has the eccentricity factor inside it, so you don't really want to so-called deal with it. Okay, so or rather you won't once the temperature is known, once the eccentricity factor is known, that thing A of T is practically a constant. So A and B are practically constants here because the temperature and pressure are constants. All right, so this thing comes from Sandler's Thermodynamics textbook. So this is the formula that comes from there. If you're interested, yeah, you can look up resources online, like the how this was actually done. There's a lot of polynomial algebra which I will just skip. Okay, so the solution procedure to solve for z. Okay, how do you solve for z? You use a cubic equation formula. So, and then once you find out the cubic equation formula, because A and B, all these are constants, so 1 minus b is a constant. A minus 3b squared minus 2b, these are constants. A, b, b squared, b cubed, these are constants as well. So you solve this cubic polynomial formula and you get out z. Okay, z is PV over RT, right? So once you get z, you know P and you know T and you know R, you will get the molar volume. So the difficult part is actually solving for z. Okay, so how do you solve for z? So we have to look at a cubic formula, and if you want to derive things yourself, you can actually assume that your cubic formula has 3 roots, A1, A2, and A3. What you do is to multiply this equation out, and you see, and you compare it with a typical standard form of a cubic formula, and then you compare coefficients. I'm not going to do it here because formulas have already been done. So what you will find out after comparing coefficients is that you will get 3 simultaneous equations with 3 unknowns. You solve them and you find out your roots. Okay. In general, A1, A2, and A3, these are complex numbers because cubic equations either have 1 real root and 2 complex conjugates, or 3 real roots. Okay, the real roots can be equal, or the real roots can be distinct. Okay, a lot of it depends on the so-called discriminants. Okay, so I'm not going to go through the derivation of that. I want to jump straight into the programming part as soon as possible, as long as we are done with the theory. So what is the equation here? The equation we are looking at here is a standard form of a cubic equation. Okay, I took this from Perry's Chemical Engineering Handbook. Some of these formulas, or in fact, these formulas here, they're from Perry's Chemical Engineering Handbook. So you have x cubed plus bx squared plus cx plus d. This is a standard cubic equation formula. So how do we start calculating the roots? Okay, first we calculate some kind of discriminant term. This discriminant term is r. And this discriminant term is r. Okay, so okay, this discriminant term is r. Hold on, I think I need to make some corrections. Okay, over here I said that for temperature and pressure and temperature is easy. So I forgot to actually edit just now. Okay, for temperature you need the volume, and for temperature you need the volume and pressure. Okay, solve for a quadratic equation in what? Square root of t. So that's what you'll need to do here. Compared to cubic equation, that'll be pretty straightforward. So this is what we covered just now. So I'm just making a note. Okay, so over here, we'll go back here. So we have this discriminant called r. Okay, r is equals to p over 3 cubed plus q over 2 cubed squared. All of this is actually derived from all that simultaneous equation thing we're talking about here. You can pretty much find the same thing. However, this from Perry's Chemical Engineering Handbook, there's a little bit of math wizardry that allows you to come at it to this conclusion. So okay, so for this cubic equation, x cubed plus bx squared plus cx plus d, you have p. Okay, this p is defined in this r term here. It's very important. It's 3c minus b squared. Q equals 27d minus 9bc plus 2b cubed over 27. So all this you can kind of program it in a function or something. So let's first explore the case where we have 3 real roots. If we have 3 real roots, our real roots will be in this form: xk equals to yk minus b over 3, where yk is this very long thing here. Okay, is this a cosine term? Okay, this cosine term, according to that formula, we'll have a phi by 3. Okay, phi is actually an expression in q and p. So let me write down what phi is. I forgot to write it just now. Okay, let me write that down. Okay, and phi equals to cosine inverse. Let's see whether this renders correctly. Cosine inverse, and I'll need to bracket it. Cosine inverse, yes. Oh, cosine inverse what? There's a square root term. So this again looks doesn't look too savory, but you know, we'll deal with it. Okay, so q squared over 4, q squared over 4 divide by minus p cubed over 27. So this is what we have here. Okay, I don't know why Paris Chemical Engineering Handbook, you know, does not, you know, do change this around. But I guess as you see here, you see this p over 3 cube and this p cube over 27. This sort of kind of corresponds, because 3 to the power of 3, that is a 27 term, so that ends up in the bottom. Q over 2, q squared over 2 kind of ends up in the top, and then you can have this cosine term where you can find your phi. Okay, so that's your phi term here, where you have 2 real roots, or 3 real roots, excuse me. So you have phi here, which is this cosine inverse of this whole term here. And if q is more than 0, we'll have this expression for yk. That's why you have this minus and plus sign here. If q equals is more than 0, yk equals to minus 2. Then you have this square root thingy, minus p over 3 cosine this number here. Otherwise, yk equals to 2 square root minus p over 3 cosine all of this here. Now p is this thing here, which may or may not be positive, but we'll find that out later. And as you can see here, there is minus p over 3, so that is hold on. So this thing here, we'll have to find out whether it's actually positive or negative. We might have to deal with complex numbers, we might not. But I mean, by having this minus sign here, it already looks like, hey, you might have complex numbers. So that's something we may have to deal with later on. Okay, but yeah, it's not always the case. P can be negative in some cases, depending on that. So we'll have to look at some of these numbers later to try and make sense of them. Now, so these are the formulas, at least for the r less than 0 case. There's a r more than 0 case as well, and there's another bunch of formulas to throw in. But yeah, let me just quickly write them down before we go to the next video. Okay, so the real root is y1. Okay, y1 is a plus b. Okay, a plus b, then we'll have these formulas. Minus q over 2 plus square root r minus q over 2 minus square root r. So that's a and b. And we'll have the complex roots as well, which I'll just quickly write. Yep, so here is the case where r is so-called more than 0. Okay, r is more than 0. Here's the case, there's the algorithm where r is less than 0, then we have 3 real roots. Okay, so we can see that over here, based on this expression for 3 roots, let me put this in the center. Based on this expression for 3 roots, we have y1 equals a plus b, y2 equals to this real part and this complex part. I here is a complex number, or the imaginary number, rather. Okay, so these are complex conjugates of each other. So you see the real parts are equal, and yeah, the imaginary part is just the opposite, so to speak, the negative of each other. Okay, so if r equals 0, expect 3 real roots. Okay, if r equals 0, a equals to b. You'll see that a equals to b right here, so the imaginary parts cancel out. So y2 equals to y3, and then y1 equals to a plus b. So if a plus b minus half a plus b equals to a plus b, then all 3 are equal. Okay, so that's how we can run this algorithm. Now, how to derive it, I'm not going to go through it, but we will want to code it. And we have some questions here as well. Okay, based on the formula I got from Perry's Chemical Engineering Handbook, we see this term 120 right here, 120K. So is this 120K a degree or radian thing? Okay, so these are the kind of things we'll have to find out, because some formulas from the textbook, they do not give you units, and based on that you have to kind of do your own testing. Now that's extra work, and that's why you always want to put units there. Okay, you always want to put units there. So let's me just show you. Maybe we'll have to do some testing, right? Maybe we'll have to do some testing with existing code that has figured out this cubic formula. And then if you want to rewrite something in Rust, well, we'll have to do some tests. Now, why am I running you through all this process? Is because you can see from here, based on the way we sort of deal with these numbers, we can see that this R term is very important. This R term will actually determine how we solve for the roots. Okay, if R equals 0, then we solve it like that. If R is more than 0, we solve it like that. If R equals to 0, we solve it a certain way as well. So you can see there's an if-else statement over there already, and we can always write that in Rust. Okay, again, if a Q is more than 0 or Q is less than 0, we'll solve things, a certain way. You will have roots being shown in certain ways. So that is going to be some of the things we need to kind of do. Okay, of course, for our purposes, okay, for Peng-Robinson equation of state, we are not really interested in imaginary roots. Okay, we are not interested in imaginary roots. We just want the real root. Okay, we want the real root. So, in fact, we might not even have to deal with complex numbers at all. So this is something we can do away with. Okay, for this case only. So we'll not deal with complex numbers because we don't have a complex volume. That doesn't make any physical sense. But yeah, this we can just use the real root, okay, and that would help us with our equation solution. Okay, we are always guaranteed a real root with a cubic equation of real coefficients, and in this case, it is a real. All of these are real coefficients. So yes, we have several questions. One is, is this 120K, 120 times K term here, is it a degree or radian thing? Okay, so we'll need to actually do some testing. Second thing, we'll know that testing is really important. If we want to code our own code from scratch, our own simulations from scratch, we'll need to do some code verification as well. Similar to how we were talking about, even the Newton's law of cooling case. With the Newton's law of cooling case, we expected, to have some analytical solution that will actually form the basis for code verification. Okay, for this code here, we might want to use some free and open source software such as GNU Octave. I have that installed already. Okay, GNU Octave right here. I can do a clear. So it is pretty much almost like MATLAB, but it's a free version. So you just use it as it is, GNU Octave. And GNU Octave has this function called roots. Okay, roots will help you to find roots of a polynomial equation. So if we have, okay, let me just write down this equation. All right. If we have this equation, okay, x cubed minus 7x plus 7 equals to 0. Okay, this is another example. Okay, this is in fact a textbook. Okay, textbook example. We got from Perry's again. You can do it with others. We can. So these are test cases. Okay, test cases. Let me go. Okay, so these are test cases for cubic solving. So let's use GNU Octave to find out the roots. So the coefficient of the first term is 1. The coefficient of the second term, which is x squared, is 0. Third term is -7. Fourth term is 7. So I'm going to put the matrix or an array of numbers. So this C equals to, okay, remember to define a polynomial here, so to speak, we just actually list out the coefficients. Okay, we just list out the coefficients. Okay, the first coefficient is 1. The coefficient of x cubed is 1. So the first term here is 1. Okay, the second coefficient of x squared is 0. Okay, coefficient of x is -7. Coefficient of x to the power of 0, that's 1. That's just 7. So we have a C term here which describes all the coefficients in our polynomial. To find the roots, we just use the roots function and put C in as an argument. We will get the roots here minus 3.4089, 1.6920, 1.3569. Okay, these are approximate roots, but this will be a good basis of comparison. I'm going to copy and paste this right here. Okay, I believe I should be able to do an array. Okay, I'll use the matrix thing here, 1, 2, and 3. Okay, and that will give you the root. Okay, so I'll put these roots in a matrix. So that's how I just put it. Roots equals to this matrix here. Okay, so these are the 3 roots. I can just swap things around. I can do a second test case. Now I'll just put an x squared term as well. Okay, 8x squared. And then I'll put a 9 over here. Okay, so 1, 8, -7, and 9. Those are my coefficients. Okay, C equals to 1, 8, -7, 9. Okay, roots of this. Okay, we will have a complex conjugate version. So this will be a good test case for our algorithms. Okay. Roots equals to, okay, the matrix of this. I'll paste this here. Okay, 1, 2, and 3. These are complex roots. Okay. I'll just delete the 0i because it doesn't look so nice. And maybe I will put it as a column vector so that's a little bit more pleasant to read. Okay, there we go. Column vector. So this will be our real root. This will be our complex roots. So at least we have 2 test cases with which to test our code. So we'll have good references with which to start. Okay, those are very important if you want to actually code. We always need to do some testing. So we will need some verification tests to ensure our code works correctly. All right, so these are some verification tests to ensure our code works correctly. If we have those verification tests, well, and we code everything correctly, if we code everything correctly, then the correct results should come out. Okay, the correct results should come out. And we see here already this is a imaginary case. So in that case, in this case, we can actually already test for our R term here. This should be a R less than 0 case. So using these test cases, we are able to sort of probe our code to see if things actually function correctly. And I can show you more of how to do test cases in Rust. But this is a general thought process. Whether you're doing Rust or any other kind of code, you will need to sort of have, of course, your your formulas well thought out. You should ideally write them down first. Normally doesn't happen if you are rushing through a project, but we'll need a test case as well. It is very, very important to make sure your basic code is functioning correctly. All right, so this is done using GNU Octave. We can use other test cases as well. That's totally fine. But having this around actually will help to determine if our code runs correctly. We can even if we don't do a complex number, we can still test whether the coefficients of the complex number are worked out correctly. Okay, so anyway, I'll stop here. Okay, this is all the whole thought process of how to even solve cubic equation and cubic polynomials here. So once you solve the cubic polynomials, you'll be able to solve for our volume. Okay, and of course there are a few ways we can do it. Again, we can use roots. Well, not these roots, but this is how you type roots in typst. Yeah, how you find these roots in Rust. Okay, there's already someone who has done all this. This is released under the BSD2 clause license. It's open source, available for commercial use, so on and so forth. So credit to Vorot. Okay, if you actually look at his, it's Mikhail, I think, Vorotilov. Sounds Russian, but yes, this person has kindly given us the code for use. So this is one of the things we can sort of find in Rust. Okay, this root finding algorithms. So anyway, I'm gonna stop here before I keep talking on too much. So that's it for today. I'll see you next time.